All right, friends, welcome back. In this video, I'd like to go ahead and move on in Chapter 3 and take a look at the next section of your textbook, which is Section 3.2, and we're going to begin to talk about polynomials in general and also the graphs of polynomials. So let's get started with that. So first of all, a really quick definition for what a polynomial is, just so that you know one when you see one. A polynomial is an algebraic expression that can have three different types of things in its structure. So it can have constants, so those are numbers with no variables. It could have variables, and it could also have exponents on those variables. Okay. So a couple of things about what polynomials are not. You will not see any division by a variable. The exponents that you see in the polynomial only can be integers, so any number from 0 to all your counting numbers, basically. And then it says here that you can only have a finite number of terms. You can only have a certain number of terms. You can't have infinitely many, okay? So a really quick picture for what a polynomial looks like versus what a polynomial does not look like. Again, the reason that this over here on the right is not a polynomial is because it has a negative exponent. And then over here we are dividing by a variable, so that makes them not polynomials. But this would be an example of a polynomial right here, where you can see that it has variables, exponents, coefficients, and just basically different terms in your polynomial. Other definitions that I want you to be familiar with, right? We often talk about the degree of the polynomial, and that is just the largest exponent on a variable. So, for example, over here you have 4x to the third plus 2x squared minus 7. That would be a degree 3 polynomial because the largest exponent is 3. Coefficients, when I say the word coefficient, what I'm talking about is the numbers in front of the variables. So here we have a couple of examples of your different coefficients of 4, 2, and 7. And then we also coined this term of the leading coefficient. If you were to write the polynomial in standard form, which means that your exponents are in descending order, then the leading term would be the term with the highest exponent on x, and then the number in front of that term, that's called your leading coefficient because it kind of leads the charge. Speaking of standard form, depending on your type of polynomial, whether you have a linear or a quadratic or a cubic or so on and so forth, writing it in standard form is definitely something that we do want to make sure you are able to do, because some certain things about the graph are going to depend on your ability to take a polynomial and rewrite it in standard form and be able to point out what the degree and the leading coefficient is. So let's go ahead and get some practice with that here in example 1. It says simply determine whether each function is a polynomial function. If so, write it in standard form, state the degree and type and leading coefficient. So if you look at part A here, it says f of x is equal to 5x minus 2x to the third plus 8. This would be a polynomial because the only thing that we see are constants, variables, and exponents. We don't see any division by a variable or any negative exponents or anything like that. So this is your pretty classic example of a polynomial here. We do need to rewrite this in standard form. So that means that the largest exponent that we see, which if I'm looking at this, I'm thinking that is going to be this exponent of 3, that will need to come first whenever we write out the function formulas here. So I'm going to rewrite this as f of x is equal to, that term is going to be negative 2x to the third because sitting in front of that 2 is a minus sign, and then we'll follow up with a positive 5x, or in other words plus 5x, and then we'll follow up with that very ending term, remembering that that term 8 does not look like it has an x on it. Secretly, it actually does. It would secretly be just simply x to the 0 power, but we typically don't write that because anything to the 0 power is just 1. We call that the constant term of your polynomial. So there would be your standard form. The degree, of course, here we'll just go ahead and abbreviate DEG for degree. The degree here, of course, again, is the largest exponent that you see on an x, and here that is 3. And then the leading coefficient, which I'll also abbreviate LC, that again would just be the coefficient of that leading term. And so here you can see that is simply just going to be negative 2 as our leading coefficient for that example. Okay, here in the next example here, we're just taking a look at this and seeing if this is a polynomial. Again, the things that you need to look out for here, are you dividing by variables? Do you have any exponents that are negative? Are there infinitely many terms? All these things would mean that you do not have a polynomial. And here I think we're good to go. There is some weird stuff here, like a coefficient of the square root of 2, maybe a coefficient of negative 0.8 is something that is kind of calling your attention there. But these are perfectly fine when it comes to a polynomial. We just want to go ahead and take this polynomial here and write it in standard form, which means all the terms that have an x have a descending order when we list those exponents here. So I'm going to pick up here with a positive square root of 2x to the fourth, and then after that we'll pick up with our minus 0.8 x to the third, and then we'll pick up with our constant term of minus 12. So there's your standard form there. Of course, now that it's in standard form, we can go ahead and look at that leading term and notice that its exponent is 4, and the number in front of it is the square root of 2. So when we go ahead and point out the degree here, that is going to be 4, and the leading coefficient here is going to be the square root of 2. Here in this next example, part C, the reason that this is not going to be a polynomial is because I see that I have a term with a negative exponent in it, okay? And so we'll just basically write the conclusion, not a polynomial. Next example over, that's part D. That's k of x is equal to x squared plus 3 to the x power. This is not a polynomial because, again, for a polynomial to be a polynomial, the exponents have to be integers, okay? And here we see that we have an exponent that is actually a variable, and so that creates a problem for us, and so we'll just go ahead and conclude here that this is not a polynomial either. So your ability to know a polynomial when you see it, and then if you have a polynomial, be able to pick out its degree and its leading coefficient is really, really important for being able to describe what the graph of that polynomial function actually looks like. And one of the key characteristics of the graph of a polynomial is something that we actually call end behavior, okay? And so end behavior has to do with just that. When you graph the function, we're talking about the ends of the curves where you put the arrowheads in these pictures. And I would just want to go ahead and explain a little bit of language that we're going to be using as we describe end behavior for the rest of the video and for the rest of class here, right? So basically the idea is this. You talk about the input and output relationship of your function, right? So it's going to say this. It's going to say as x gets larger, or they're going to use some symbols here, and they're going to say as x arrow infinity. So basically that is mathematics notation for being able to represent that idea of x is getting larger and larger and larger in value. And don't forget that x is actually the input, okay? In terms of the graph, that means x, of course, that is our horizontal axis, right? So when we say that x approaches positive infinity, we mean that as x gets further and further and further to the right, or we could also say as x approaches negative infinity, that idea would be as x gets smaller and smaller and smaller, or in other words, as we're moving further and further to the left on the graph, okay? So as this happens, we're going to describe what the outputs are doing. So as the outputs get bigger, or as, let me rephrase that. As the inputs get bigger, or as the inputs get smaller, are the outputs getting bigger, or are they getting smaller? That's how we're describing end behavior here. So it says, what does f of x do? Or in other words, what does the output do? Do we rise further and further up? Do we rise further and further down? That's the case, right? And so if you think of all the different possibilities, here's just a quick table that just kind of summarize all those things. What we basically need to look at in all cases is what is the degree and what is the leading coefficient of your polynomial. If you're able to rewrite your polynomial in standard form and then pick out these values, then you're always going to be able to figure out what the end behavior of your polynomial actually looks like based on whether or not your degree is even and whether or not your leading coefficient is negative, okay? And so the easy way to remember this is I want you to first look at the situation where you have two ends that both point in the same direction. Maybe the ones that I circled there that both point up, or maybe the ones that I circled down here that both point down, okay? If your end behavior points in the same direction on both ends, then that means that your degree is going to be an even number, okay? So that's pretty easy to remember. Again, if you have two ends that point in the exact same direction, you're going to have an even degree, okay? And if you look at the coefficient there, in the case where they both point up, you have a positive leading coefficient, and that's easy to remember, positive direction going up. And in the case where you have a negative leading coefficient, that means you have two ends that both point down, okay? So that means if they both point in the same direction, that's going to be an even degree, and you follow the leading coefficient sign to determine what direction they follow, okay? In the case where you have a degree that is odd, this is where you're going to have two ends that point in different directions, right? So maybe one end points down while the other points up, okay? And the whole difference between the leading coefficient being positive or negative, the way that you can remember this is if the leading coefficient is positive and the degree is odd, then the ends are going to point in different directions, but overall, you kind of look at this as a roller coaster. You are basically climbing as you go from left to right on that function. That is a way that you can kind of remember that this is a leading coefficient that's positive, is because overall we're climbing, whereas over here in this other situation, if the leading coefficient is negative and the degree is odd, then overall you are sliding down the slide, okay? You're going downward overall, okay? Now again, in order to describe this, you'll see what they've written there. they're saying that f of x arrow positive infinity, or in other words, as the outputs, or sorry, we'll say this, as the inputs get bigger and bigger and bigger and bigger, we can say this, right? The outputs are going to get bigger and bigger and bigger. So basically, the further right we go, the further up we go in this situation. And you can see this down here, right? As x approaches negative infinity, or in other words, as x gets further and further and further to the left, then f of x, the outputs, that is approaching negative infinity as well. So basically, the further and further down we go. So basically, the way to say this in plain English would be the further right we go, then the further up we go, and also the further left we go, the further down we go. Okay, that would be a way to say it in kind of plain English. And I'll let you go ahead and think about how you would kind of translate that language to these other situations here. But this is exactly what we want to go ahead and look at as we take a look at problems concerning end behavior, the degree and the leading coefficient. So like here in example 2, it says, describe the end behavior of the graph of the function and make a sketch of the shape of the graph. Okay, we're actually going to go ahead and skip sketching the overall shape. We will go ahead and sketch a quick idea of what the end behavior would look like. Okay, so here in this first example, right, we have here a leading coefficient of, it looks like negative 0.5, and that of course is a negative number, whereas the degree of this polynomial, the highest exponent that we see after it's written in standard form, is a 4. Okay, well here we're just going to go ahead and point this out, right? So the degree here, that is an example of an even number. And so because of that, we know that we're going to have two ends that either both point up or they're going to both point down. To determine which one, we take a look at the leading coefficient here, and we would see here that the leading coefficient is a negative number. Okay, so that means that overall we're going to have two ends that both point down, and that would be good enough for being able to kind of describe that end behavior. We don't quite know what the middle of the graph would look like, so in other words, we don't quite know, what the roller coaster path would look like here, if it's just straightforward going across, or maybe if it kind of comes down and comes back up and back down or something like that. We just know what the end behavior is doing based on this information. In this next example here, we see here that the leading coefficient is a positive number, and the degree is an odd number, and so that means the degree is odd. We're going to have two ends that point in different directions, and the leading coefficient is positive, so that means that overall we're climbing. So that means that we're going to be climbing, and again, we don't know what the middle looks like. We don't know if it's just straightforward connects, or if it maybe comes up before coming back down, or maybe if it does, a whole bunch of up and down, but we do know what the end behavior is doing in that graph there. Next example here, the degree is 2, which is even, so they were both going to point in the same direction. The leading coefficient is positive, so that means that we are going to have two ends that both point upward, okay? So very, very easily done. And then here in this last example here, check to make sure that that's in standard form. It looks like all the exponents on x descend as we read from left to right, so that's good. So that makes this the leading coefficient there of -2, and then we have a degree 5. So that's going to be an odd degree, so different directions, and then a negative leading coefficient means that overall we're going to be falling. So that means we're going to start off high, but then eventually as we read from left to right, we're going to end low. So again, we don't quite know what the middle looks like here, but we do know that we're going to be falling as we go throughout in general. So that's just a quick way to kind of describe the end behavior given the function formula. Maybe let's go the other way around. Maybe I give you the graph, and then from this you have to pick out what the degree would be and what the leading coefficient would be. Well, we won't be able to figure out what those actual values are going to be, but we can see here that the end behavior looks like as we go further to the left, I'm going further down, and then as I go further to the right, I'm going further up. So I have two ends that point in different directions, and it looks like overall I'm climbing on this roller coaster as I read from left to right. So that is going to mean that the degree, of course, since the ends are pointing in different directions, the degree is going to be an odd number, whatever that value is. And then the leading coefficient, which I'll just abbreviate LC, we know that that is going to be a positive number in general because I am climbing overall. On this next example here, it looks like I have two ends that both point down, and so that is going to mean that I have a degree that is an even number. Whatever its value is, it could be 2, it could be 4, it could be 6, it could be any even number as far as we know. And then overall, let's find out what we're doing here. So it looks like they're both pointing in the downward direction, and so that is going to mean that the leading coefficient, of course, is going to be a negative number. Okay. Another way we might describe that is the further left we go, the further down this graph goes, and then the further right we go, the further down this graph goes, okay? So being able to kind of read through that language that we talked about a little bit ago. So being able to determine the end behavior is the only goal for this video, other than just kind of reviewing what a polynomial is and how to find its leading coefficient and its degree. So we're going to go ahead and call it there for the video. So thank you very much for your attention. If you guys have any questions, then feel free to let me know, but that's all I have for this one. I will speak to you in the next one.